A timeless fascination, time travel in our minds. From H.G. Wells's The Time Machine to the iconic DeLorean in Back to the Future, time travel has captivated our imaginations for over a century. The idea of journeying through time, witnessing historical events, or even altering our own past holds an irresistible allure. But can this staple of science fiction become a reality, or is it destined to remain a figment of our collective imagination? The allure of time travel lies in its power to fulfill our deepest desires and confront our greatest fears. It offers the tantalizing possibility of righting past wrongs, reliving cherished memories, or glimpsing the future that awaits us. Yet it also raises profound questions about the nature of time, the paradoxes of causality, and the limits of human knowledge. To comprehend the possibilities and limitations of time travel, we must first delve into the groundbreaking work of Albert Einstein, whose theories of relativity revolutionized our understanding of space and time. Einstein's insights were not just theoretical, they had profound implications for how we perceive the universe. Prior to Einstein, time was considered an absolute, an immutable backdrop against which the events of the universe unfolded. This Newtonian view held sway for centuries, shaping our understanding of physics. Einstein shattered this Newtonian view, demonstrating that time is not absolute but rather relative, dependent on the observer's frame of reference. This was a radical departure from the established norms. One of the most startling implications of Einstein's theories is the concept of time dilation, which states that time slows down for objects in motion relative to a stationary observer. This phenomenon has been confirmed by numerous experiments. This effect, while negligible at everyday speeds, becomes increasingly pronounced as an object approaches the speed of light. For instance, astronauts traveling at high velocities would experience time differently than people on Earth. In essence, time is not a constant, but rather a variable, intricately intertwined with space to form the fabric of the cosmos, what we call space-time. This interconnectedness opens up fascinating possibilities for the future of space exploration and our understanding of the universe. While Einstein's theories provide a theoretical framework for time dilation, they do not explicitly forbid the possibility of time travel. His groundbreaking work on the nature of space-time has opened up a realm of possibilities that were once confined to the realm of science fiction. One intriguing concept that emerges from Einstein's equations is the notion of wormholes, hypothetical tunnels that connect two distant points in space-time. These wormholes, if they exist, could theoretically allow for instantaneous travel between far-flung regions of the universe. Imagine folding a piece of paper in half so that 2 points on opposite ends touch. This simple analogy helps us visualize how a wormhole might function, bending the fabric of space-time to bring distant points into close proximity. A wormhole, in essence, would be like punching a hole through the paper, creating a shortcut between those 2 points. This shortcut could potentially allow for travel across vast distances in a fraction of the time it would normally take. While wormholes remain purely theoretical, their existence is not prohibited by the laws of physics as we currently understand them. The equations of general relativity suggest that such structures could exist, even if we have yet to observe them directly. If we could create or manipulate wormholes, they could potentially serve as gateways for time travel, allowing us to traverse vast distances across space and time. This would revolutionize our understanding of the universe and our place within it. However, the technological challenges involved in such an endeavor are so immense as to make it seem like an impossible dream. The energy requirements alone would be astronomical, and we are only beginning to scratch the surface of what might be possible. Another avenue for potential time travel emerges from the bizarre and counterintuitive realm of quantum mechanics, the theory that governs the behavior of matter at the atomic and subatomic level. In the quantum world, particles exist in a superposition of states, meaning they can be in multiple places or states at once until observed or measured. This inherent uncertainty and probabilistic nature of quantum mechanics have led some physicists to speculate about the possibility of quantum time travel. One intriguing concept is quantum entanglement, where two particles become linked, even across vast distances, so that the state of one particle instantaneously affects the state of the other. Could this interconnectedness at the quantum level somehow be harnessed to influence events in the past or future? The answer remains elusive, but the possibilities are tantalizing and continue to fuel scientific inquiry. Section 5, Paradoxes and Puzzles, the Grandfather Paradox. While the prospect of time travel is undeniably captivating, it also raises a host of perplexing paradoxes and logical inconsistencies. One of the most famous is the Grandfather Paradox, which posits that if you were to travel back in time and kill your grandfather before your parent was born, you would prevent your own existence, creating a logical contradiction. If you never existed, how could you have traveled back in time to kill your grandfather in the first place? The Grandfather Paradox highlights the potential for causality violations, where an effect precedes its cause, creating a temporal loop that defies our understanding of cause and effect. While some physicists believe that time travel may be possible without violating causality, others argue that such paradoxes demonstrate the inherent impossibility of altering the past. Section 6. The Arrow of Time. Why can't we remember the future? This question has puzzled scientists and philosophers for centuries. Another challenge to time travel lies in our understanding of the arrow of time, the concept that time seems to flow in one direction. The seemingly unidirectional flow of time from past to future is something we all experience daily. While the laws of physics do not explicitly forbid time travel in either direction, our everyday experience tells a different story. There is a clear asymmetry in our experience of time. We can recall past events but have no memory of future ones. We have memories of the past but not the future, and this is largely due to the way our brains are wired. Entropy, a measure of disorder, tends to increase over time, making the past more ordered than the future. This arrow of time, deeply ingrained in our experience, is a fundamental aspect of our universe. It poses a significant obstacle to the possibility of traveling back in time, as it contradicts our natural perception. Some physicists speculate that the arrow of time may be a consequence of the initial conditions of the universe, specifically the low entropy state of the Big Bang. At the moment of the Big Bang, the universe was in a state of low entropy, which has been increasing ever since. As the universe expands and evolves, entropy increases, creating the arrow of time we observe. This increase in entropy is what gives us the sense of time moving forward from a state of order to disorder. If this is the case, then reversing the arrow of time may be as implausible as unscrambling an egg. The concept of time travel remains a fascinating topic, but the arrow of time presents a formidable challenge that we have yet to overcome. Section 7. Time travel today, experiments and possibilities. Despite the theoretical and practical challenges, scientists have not given up on the dream of time travel. While we are far from building a time machine, researchers are exploring the boundaries of time dilation and quantum entanglement, searching for even the slightest hint that time travel may be possible. Experiments involving atomic clocks flown at high speeds have confirmed Einstein's predictions of time dilation, while quantum entanglement experiments continue to push the boundaries of our understanding of interconnectedness. While these experiments are still a far cry from sending humans through time, they represent important steps in our quest to unravel the mysteries of time. Each new discovery brings us closer to understanding the true nature of time, and whether we can ultimately transcend its seemingly insurmountable barriers. Section 8. The Future of Time Travel, Dreams and Dilemmas. The possibility of time travel raises profound philosophical and ethical questions that extend far beyond the realm of science. If we could travel through time, how would it change our understanding of history, free will, and the meaning of human existence? Would we be tempted to alter the past, even if it meant erasing ourselves from existence? And who would have the right to control such a powerful technology? These questions, while hypothetical for now, underscore the immense responsibility that would come with the ability to manipulate time. Time travel, if it ever becomes a reality, will not only be a scientific marvel, but also a profound philosophical and ethical challenge, forcing us to confront the deepest mysteries of our existence. Section 9 conclusion: the undiscovered country. Time travel remains one of the most tantalizing and enigmatic concepts in science fiction and theoretical physics. While Einstein's theories of relativity provide a framework for understanding time dilation, and quantum mechanics hints at the possibility of temporal anomalies, the practical and paradoxical challenges of time travel are immense. Whether time travel will forever remain a figment of our imagination or ultimately become a reality is a question that only time, the ultimate arbiter, can answer. For now, the undiscovered country of time travel continues to beckon, inviting us to explore the boundaries of what is possible and to ponder the profound implications of venturing beyond the familiar flow of time.